All right, welcome to lesson 2A for EE301. If you're wondering where these lecture notes are coming from, if you go to the EE301 course website, if you just search EE301 in Google, it's likely to come up. Under the summer syllabus, the third one down right there, summer syllabus, will show you the schedule for where we are moving through all of the material, but then down here, under each of the lessons, we have the PowerPoint file, the lecture notes, and the video links, which I'll be uploading after I make this video. So lecture notes, resistance, and Ohm's law is lesson 2A. That is what I have open right here. So now we can begin talking. We left off after lesson 1 with voltage and current, voltage being V, current being I. And we said that electricity was about the movement of charge, and I was the rate of charge, and V was the electrical potential difference that would tell us the amount of energy needed to move that charge. So now let's talk about resistance. If I is the rate of charge, that flow of the electrons, the flow of the charge, then resistance is the opposition to that. So the opposition to the charge movement. So as the electrons are moving through, they hit other atoms along the way and they don't just move smoothly through. So in a circuit, this is the symbol for it. Typically, right now in DC direct current, we have a circuit that goes through and comes back, and it's going in a circle. The larger side is the positive side. The smaller side is the negative side. This is a DC voltage source. So the electrons are coming in the conventional current flow like this. So the charge is moving, I, and it comes through. And there's 3 parts to every circuit from here until the very last lesson, which is that we need a source, a path, and a load. And so this is the first load that we're looking at, is a resistor. Now, there's also resistance inside of just the materials. If you think about, you look outside the window, I can look outside the window right now and see the electric lines. And so as the electricity flows through it, there's different materials that the electricity can flow through. And depending on what the material is and the size of it, there's what we call internal resistance to the line. It doesn't all get to your house when it leaves the power plant, you know, a few miles away. It goes through these electric lines, and there's internal resistance to the line. So this resistance can be measured with this formula right here, which is also on the equation sheet. So if I look at the equation sheet, we've talked about charge, we talked about voltage, we talked about current, and here is the resistivity, or the resistance. So resistivity is rho, and it is a material constant based off if I had steel that was carrying my current, if it was copper, whatever it is, it has its own constant there for rho. L is its length, as you can see along this line right here. And then A is a cross-sectional area in circular mils. So let's talk, what is a circular mil? Here's a formula for it. If we have a diameter in mils, which 1,000 mils makes up an inch. We can kind of see that right here, 1 times 10 to the negative 3 inches. So 1,000 mils equals 1 inch. And if we take that number, we square it. But really, what is it? It's kind of harder to visualize. There's a table of resistivity. And now let's look at a picture to kind of help us think of what a circular mil is. Big C, big M is a circular mil, not centimeter. And you can see that if I knew how wide it was in mils, knowing that 1,000 mils makes up an inch, and I can visualize kind of a wire, or one large wire made up of several smaller ones. And so that's what it's telling us, is in circular mils, it's an area that we don't have to worry about calculating pi r squared and all that jazz. We can just take it as a circle for a wire and put it in circular mils. So back to the lecture notes. We see it's not a centimeter, it is a circular mil. So now let's do example 1 here. We're given several things. We have length, that's that L inside that formula. If I'm looking at my resistance formula, we're looking for resistance here. R is equal to rho L over A. Do we have L? Yes. We have rho? Yes. Do we have A? No, but we do have a diameter. So let's put the diameter into mils. And if I have 1/50th of an inch, railroad track that, and I say that there's 1,000 mils inside of 1 inch. The inches cancel out, and I get 20 mils. Well, that's still just a diameter, but we said all we have to do, don't worry about pi r squared. All we have to do for A is that we can square that. 20 squared gives me 400 circular mils. That's all we got to do. So now we can plug in the rest of this formula. 10.37 cm ohms. Ohms is the unit for resistance. That's what we saw up here, right? Unit of ohms. That omega symbol is ohms. And so we're searching for that. That's going to be the last one. It's not canceled whenever we put all these in. Circular mils, ohms over feet. We multiply it by the 1,000 feet. We multiply that, or rather we divide it, because we have A, rho L divided by A, and A there is 400 cm. Cm cancels out, feet cancels out. I multiply that through my calculator, and I'm left with 25.925 ohms. There's example 1. Let's keep moving down. So this is what a physical resistor looks like. And since we're in, if you're in an online environment, you won't actually handle these. But if we were in the class inside of Rickover, we actually do solder some resistors together. And this is just telling us how to read them based on the colors. And so the colors have different values that they represent, and they mean different things. And this one is a 4-band resistor. You can see 1, 2, 3, 4 bands. And so each of these descriptors right here, the first digit is the first digit of the number. The second band is the second digit. And this one here is a multiplier. So it's multiplying it by something, and this is its tolerance level. Nothing's perfect. I mean, if you're looking at like a high expensive aircraft with really specific circuitry, you may want a tolerance level of 0.01 to make sure that it is exactly what you need for the circuit. But if you can also just, the ones that we use in class usually have like plus or minus 10%. And here's what these are saying. So the plus or minus 10% would be silver, plus or minus 5% would be gold. And if there is no 4th band, if you're looking at a 3-band resistor, then its tolerance would be 20%. So just using the method that we saw of the first digit, second digit, multiplier, and the tolerance, we can put these together. And I'll zoom out just a little bit so we can see the colors there. So the brown is a 1. The black is a 0. The brown of the multiplier, because we're on the 3rd one now, this one right here is the multiplier. So this is like saying times 10 to the 1. Times 10 to the 1, so it adds another 0 on it. And then the gold right there says plus or minus 5%. So 10 times 10 to the 1 gives me 100 plus or minus 5%. That's in ohms. You can do this next one. The green is a 5. The blue is a 6. The yellow, it's a 5-band resistor, and so the yellow is still another number, 564. The green is another 5, right? Right there, that one's the multiplier. Oops. So this one right here, let's say it's like saying 10 times 10 to the fifth, and then the silver is plus or minus 10%. So if I do 564 times 10 to the fifth, well, please don't write 564 times 10 to the fifth. Put it in engineering format, which would be 56.4 mega ohms plus or minus 10%. We can keep moving down along the page. I'll skip example 3, and let's move on to our favorite law in this class. Pretty much, if we ask you a question and you have no idea what the answer is, if you at least just say Ohm's law, probably 50% of the time, that's going to be right in this class. It's what we're using all the time. Right here on the equation sheet, it's this one right here, all by itself in this one big box. Ohm's law, V equals IR. Here on the notes, it says E equals IR, and that's note that E is for sources. So if we had a voltage source, in V we're going to often use as loads. I said earlier that everything needs a source, a path to get to the source, or a path from the source to get to the load, and so the V would be on the load side. So what Ohm's law is stating is that the voltage across a resistor is the same as the resistance multiplied by the current going through that resistor. So that's why it says V equals IR. So the voltage across this element down here at the bottom has a current going through it and a resistance. If I multiply that current and I by that resistance, then across that resistor, that's its voltage. So sometimes we can use subscripts, say that this was R1, then I would say the voltage across R1 is equal to the current going through R1 times R1. It's a way to make sure that you're grabbing the correct one. Because another way that I could look at a circuit is I could look at everything on the source side. Here's the load, here's my source, E, and here's my R. So if I wanted to use the E equals IR, there's only one resistor in this, there's only one current going throughout this, so for this one resistor circuit, E would be equal to IR. Note the polarities. If we are looking across this, it's going from out of the positive side, it's going to dissipate. It's going to, the resistor is going to oppose those electron flow, and so the voltage potential difference across the resistor will drop. And then positive, negative side, those line up. Whereas if we had the opposite current flow, we would have the opposite of the voltage, potential difference. Some people will get uncomfortable with negative voltage, but it's just like being in a basement. If I'm at 0, then the potential difference to go down is down into the basement. If you're comfortable with basements, you can be okay with negative voltages. So, favorite law right here, V equals IR for example 4. V equals IR. What we're searching for is I, so we'll rearrange it. I equals V over R. You might want to get used to that. Often we're searching for the current, not the voltage, and it's always V divided by R for that. So we have 16 volts divided by 2 kilo ohms, and that results in 8. But what is it going to be? It's going to be 8 milliamps. If you need to plug it into a calculator to see that, that's okay. But if you notice I have a kilo in the bottom, that's 10 to the 3. Well, since it's on the bottom of the fraction, that's like saying 10 to the negative 3 in my final answer. So 8 milliamps. We could work it the other way for example 5. Favorite law, V equals IR. I is 1.5 amps. R is 80 ohms. That results in 120 volts. So that is the voltage across that resistor. The current flowing through it times its resistance. Now these are some of the tools, and I'll let in the lab video, you'll get to play with them a little bit more. In the real world, we have these digital multimeters that measure multiple things. We can measure current, voltage, or resistance with them, and they have to be plugged in different ways. So and the main thing to take off of this page is that we always speak in voltage across. We don't say the voltage through something. It's a potential difference. So the voltage across this lamp in the circuit is across from here to here. Whereas if we were to measure the current going through it, we would have to put this current inside the circuit as well. But the current that's going to flow through this resistor is the same that's flowing through this machine, if you will, through the digital multimeter. And so we measure current through. And so throughout this whole semester, always speak at voltage across, current through. It is not current across, it is not voltage through. And if we needed to measure the resistance of something, this is talking about polarity real quick. So here's an example that I was just saying about negative voltage. If I plugged it in across right here, then it's positive. But if I swapped the terminals where the red was on the negative side, then it would read a negative voltage. Now, if you're going to measure resistance, and this is also true in our circuit simulators, but you must measure the resistance without a voltage source, because essentially this itty bitty little digital multimeter is acting like a small voltage source. So in order to measure its resistance, it's sending a tiny current through it to measure it. So you have to remove it from the circuit in order for it to measure it. If there's another voltage source inside of the circuit when you're measuring resistance, it will not take an accurate reading. Now this page has two key terms that we're going to use the rest of the semester, which is open and short circuits. Now earlier I said that all circuits need a source. So here's a voltage source, a path to get somewhere, a load that's going to take those electrons, and a path to get back. It must be completed, and it's running like a circle, like a loop, where these electrons or these charge is flowing through. And so when I have no path is an open. Open, no path, right? So I need a source, a path, and a load. And if I have a short circuit, which we use all the time, we use the term short circuit, but if you look on this picture right here, there's now no load. So a short circuit is no load, right? And so we'll sometimes see that if there is a short inside of a circuit, the electrons that we're going to flow out of here end up not ever making it to the load, and they all go through the path of least resistance. They go through the short. Nothing goes to the resistor. And so I bet right now, if you looked up 5 articles inside the Wall Street Journal, the New York Times, and the Washington Post, one of them will use the phrase short circuit. It's used all the time. And what we mean is there's something that needs to happen. And if we short circuit the process, which Wall Street Journal will use it today, I'll go look up an article. If we short circuit the process, then that means that what we needed to get power doesn't get power. What we needed to get this charge doesn't get the charge. It was short circuited. So now there's the actual electrical term for a phrase that you probably use all the time. So if we see one of these opens or these shorts on a circuit, what does that mean mathematically? If we're looking at an open, then there is no path, and what we would say is there's zero current. There's no way for these electrons that are moving along to go all the way back to the voltage and form that loop that is needed for a path. No path, it's open, but it's like an infinite amount of ohms. It just cannot get through. Whereas a short circuit would be an infinite amount of current, because when there's no load, if we're looking at V equals IR, there's no load, R is 0, then the current spikes. So current spiking is a good thing to also think about, that you don't want your body to become the short circuit. Now, you may have a little bit of resistance in you, but what you definitely never want to do is grab a hot wire on one hand and another hot wire on the other hand and make your body the short circuit. That would be an unsafe thing to do when that current goes through your heart's electrical system. So please, if you remember one thing from this class, remember to never make your body the circuit or your body the short. This last page is taking some readings. If you wanted to take those and check them with your instructor, you can, but that'll for me conclude lesson 2A.